Good afternoon, students. In the today's class, we will discuss about the program control instructions. So, in the last class, we have seen some arithmetic control instructions and load store instructions, rotate and shift instructions. All those things we have seen in the last class. So, if you want the diagrammatical explanation about the arithmetic, what is that rotate instructions and shift instructions, you better go through the the user guide of the DSP processor, which I have shown you during the initial classes. So the user guide is the one which describes the uh, uh, everything, which describes everything about the DSP processor in detail. So you just visit the user guide. Otherwise, I'll send that one in the WhatsApp group. Okay. So in the today's class, we'll discuss about the rest of the instructions which are there in the DSP processor. So actually, I told you that in the last class, we are supposed to discuss the norm instruction. Okay, now so after finishing the rest of the instructions, I'll come back to the norm instruction. Don't worry about it. Norm is nothing but the normalization. So in the present class, we'll start with the program control instructions. So the program control instructions are nothing but the instructions uh, which are taking some decision based on the condition or without checking any condition. They are diverting the execution control from one location to another location. They are diverting the execution control from one location to another location. So here we are first studying about the under the program control instructions. So we'll see about the branch control instructions and call instructions. Okay. So branch control instructions. The first one is the BACC. So in this instruction means when this instruction is getting executed in the program, then that is a DSP processor will take the accumulator lower byte content as a address. So if you see this one, if you see on the screen, we are having the what is it? BACC instruction. This particular whenever the BACC instruction getting executed by the DSP processor in the program, then the accumulator lower byte is treated as a memory location. What I mean to say that the accumulator lower byte, which is a 32-bit number, now accumulator is a 32-bit register. So in that the lower order word, which is nothing but the 16-bit number, that 16-bit number is loaded into the program counter. So means whenever the BACC instruction getting executed by the DSP processor, then the execution control will be diverted to the memory location, which is specified by the content of the lower order word of the accumulator. Content of the lower order word of the accumulator. So that value is loaded into the program counter. So we know that the program counter is nothing but the it is a register which points the address of the next instruction to be executed by the microprocessor, which points the address of the next instruction to be executed by the microprocessor. So for that we are using means the DSP processor is the one which is using the program counter. Yes. Okay. So the next instruction is the instruction B, which is a branch instruction. Okay. So whenever the B space, the syntax for the B, this particular instruction is a B space PMA, which is a program memory address. Means in this particular B instruction, means when you are taking the B instructions like this. Let me take the example. So if you are taking the instruction B, then you may specify the address or you may specify the label. You may specify the address or you may specify the label. Based on that one, it will divert the execution control. Let us suppose I'm mentioning the address 3500H. 3500H means whenever this instruction is executing by the microprocessor, then whatever the address you are specified as a part of the B, instruction B, which is a branch instruction, this value will be copied into the program counter. This value will be copied into the program counter. Means the execution starts from the 3500H onwards. Means the execution control will be diverted from here to the 3500H memory location. From the present location to the 3500H memory location. Okay. So the other way of thing is even if you want, you can make use of the one of the auxiliary register to indicate the address to where you would like to divert the execution control, to where you would like to divert the execution control. Okay, now. So here the example based on this instruction. So whenever this instruction getting executed, so the example is a PMA, that's the program memory address value is directly loaded into the program counter. So the program counter will start the execution from the specified memory location. Means whatever the content which is loaded into the program counter, from there the execution will get started. Okay, so that is about the instruction B. The next one is the CALA instruction. CALA instruction. So this instruction, when this instruction is getting executed by the DSP processor, first of all it will increment the program counter by 1, and the incremented program counter value is pushed onto the top of the stack, because we are Previously these are the branch instructions, ma'am, that is the BACC and the B instruction B. These two are the, means I just took only the two examples for the branch instructions. We have lots of means lots of instructions under the branch control instructions. So I'm not taking all of them. I just took only the two instructions. And these are the branch instructions, means branch instructions are diverting the execution control within the same program. Branch instruction branch instructions are nothing but the instructions which diverts the execution control from one location to another location within the same program. From one location to another location within the same program. But if you take the call instruction is not like that. So call instruction main intention is to call the subroutines. So the call instructions also looks like a unconditional branch instructions will, which will divert the execution control from the one location to another location. But the problem is, in the branch control instructions, the execution control transferred from one location to another location within the same program. But in the call instruction, execution control will divert from the main program to the subprogram. It will divert from the main program to the subprogram. So we have seen one pattern during the microprocessor case. Let us suppose I'm having the main program. This is my main program and this is my subprogram. Okay. Now. So let us suppose over here means I'm having the instructions over means some set of instructions are right over there, and I'm having the some more instructions over here. But between these two, I'm assuming that I'm having the CALA instruction, call instruction. Okay, CALA instruction. So as I told you that if you want to execute a particular program, I'm calling this one as a main program, right? This is a main program and it is a sub program. I'm just taking the sub S for subroutine and M for main program. Okay. So when you are executing the main program, in order to execute the main program, as usual, you are supposed to give the starting address of your program into the program counter. Means the program counter loaded with your program starting address. Okay. So it will start the execution. Okay. So once it come across the CALA. So what is the meaning of this particular instruction? Means divert the execution control from the main program to the subprogram. Or I can say that it is a call instruction. It is a call instruction which will divert the execution control from the main program to the subprogram. Okay. But when you are diverting the execution control from the main program to the subprogram, after finishing your subprogram execution, you should come back to the main program now. So when you are coming back to the main program, you should remember that from which instruction onwards you are supposed to continue the execution in the main program. So for that, what you are supposed to do, you are supposed to know the what is the program counter value just before leaving from the main program to the subprogram. So all these things means before diverting the execution control from the main program to the subprogram, what the microprocessor will do means whatever the important registers contents are there, which may be useful when it is coming back to the main program to continue the main program execution. So all those registers contents are pushed onto the top of the stack. All those registers contents are pushed onto the top of the stack. Like we may have the status registers, we may have the program counter, and we may have the some important registers content which are very important in the main program. Then all those registers are pushed onto the top of the stack upon the execution of the call instruction. So when they are pushed onto the top of the stack, then the program counter value, that is a program counter, is loaded with the new value which is specified as a part of the CAA instruction, and it will take that new value and enters into your subprogram, and it will start the execution of your subprogram. Okay. Once it is returning from the subprogram to the main program, then the DSP processor will perform the popping operation automatically without your knowledge. What the microprocessor will do means it will pop the top memory locations from the top of the stack into the specified registers when it is returning from the subprogram to the main program. We have seen this explanation during the explanation of the what is that static pro, that is a stack memory, and as well as the push and pop instructions, and also the branch control, and means we have the conditional and unconditional branch control instructions now. So during those instruction set explanation in the 8086 microprocessor, we have seen the clear picture. Okay. So during that time, so here so whenever the CLA instruction is executing, then the present program counter value is incremented by 1 and pushed down to the top of the stack. The content of the accumulator lower byte, again here the content of the accumulator lower byte is what is that copied into the program counter to continue the execution. Means the content of the accumulator lower byte is indicating the starting address of your subroutine. Okay, now let us go for that also. So yeah, CALA instruction. So if you see this one, so it will when the CLU instruction executed by the microprocessor, then the lower order word of the accumulator will be copied into the program counter, and now the program counter will start the execution. Means whatever the subprogram you have written, that subprogram starting address should be loaded into the accumulator lower word, so that whenever the CLU instruction getting executed by the microprocessor, then this value will be copied into the program counter as the starting address of your subprogram. Okay. So the next one is a CALL instruction now. CALL instruction. So this particular CALL instruction is nothing but it is a call instruction. Okay. Now previously CALA also the call instruction. CALA also the call instruction. But in this instruction case, we are not specifying the address of our subprogram as a part of the instruction, but indirectly we are specifying the address of the subprogram by loading the address of subprogram into the accumulator lower word. Means accumulator lower word register content is used as a address of the subprogram, but in the CALL instruction you are writing the memory location of your subprogram as a part of the instruction, okay. So PMA is nothing but the program memory address. Means you may specify the address directly as a part of the instruction, or you may use any one of the auxiliary register content as a starting address of your subprogram. Okay, now depending on the option which you are opting, whether you are specifying the address of your subprogram as a part of the instruction, or whether you are giving that address as a part, whether you are giving the starting address of your subprogram into the auxiliary register. So that purely depends on your interest, how you are calling the subprogram using the CALL instruction. Here also, when the execution, before diverting the execution control from the main program to the subprogram, as I told you that the program counter should be incremented by 1. In order to resume back the execution in the main program, the program counter value should be incremented by 1 and push that value onto the top of the stack. And after that, the program counter is filled with PMA value. So means the PMA value is filled into the program counter. The PMA value is filled into the program counter. Are we clear? So this is a CALL instruction. This is a CALL instruction. Okay. So let's go to the another instruction, which is a CC. It is also the conditional branch instruction. It is a conditional branch instruction, or the conditional call instruction. I can say it is a conditional call instruction because we have the two types of conditional instructions. The branching instructions are of two types. One is the unconditional and conditional. So CALL is a unconditional branch instruction without checking any condition. Whenever it is executed by the microprocessor, simply it will take the PMA address and enters into that particular program. But in case of the CC, it will, before diverting the execution control from the main program to the subprogram, what this particular instruction will do means it will check the condition. If you want, you can mention the several conditions, means multiple conditions you can indicate over here. If you are having the multiple conditions, means if you are interested to divert the execution control from the main program to the subprogram, if a certain condition is satisfied, then only if you want to transfer the execution control, then you can take the CC. So CC is diverting the execution control from the main program to the subprogram by checking the condition. If the condition is true, then only it will divert the execution control. Otherwise, it will continue with the normal instructions. What I mean to say that if I am having the main program over here and a subprogram over here, and I'm assuming that I'm having the instruction CC instruction over here. So this is my CC instruction followed by, let us suppose the starting address of my subprogram is a 3500H. And I'm giving the condition also. Okay, now I'm not mentioning all those conditions over here. If at all, this condition, whatever the condition I'm mentioning over here, if then this condition is true, then only the execution control will divert from the this location to the main subprogram, from the main program to subprogram. If at all this condition is failed, whatever the condition you are specifying as a part of the CC, if this condition is failed, then it will continue with the next coming instructions after the CC. Okay, now next coming instructions after the CC. Okay, now those instructions will get executed by the microprocessor. So this the execution purely depends on, that is a diverting the execution control from main to the subprogram purely depends on the condition. Purely depends on the condition. Okay, now. So the next case is push and pop instructions. So as I told you that what is the main use of the push and pop instructions? In order to access the stack area, we are interested to make use of the push and pop instructions. With the help of the push and pop instructions only, we are able to perform the what is that reading the data from the stack and writing the data onto that stack, or I can say that popping the data from the top of the stack and pushing the data onto the top of the stack. That can be done by the push and pop instructions with respect to the stack. With respect to the stack. So when you are taking the pop instruction, whatever the data which is there on the top of the stack. Let us suppose this is my stack area, and assume that the up to here the stack area is filled. Okay, now up to here the stack area is filled means this entire thing is a stack, and the last memory location I am assuming that this is a last memory location. Up to here the stack is filled. So when you are taking the executing the pop instruction, whatever the information is there from the top of the stack, that will be pushed into the that will be popped into the accumulator layer word. Okay, now so TOS is nothing but the top of the stack. TOS is nothing but the top of the stack. This particular top of the stack value will be popped into the accumulator layer word. But as I told you that the accumulator is a 32-bit register, na? The higher word of the accumulator is by default filled with 0. By default filled with 0. Okay, now. So this is a popping operation. Now, when you are performing the pushing operation, pushing is nothing but storing the information or pushing the data onto the top of the stack. Okay, now. So whatever the content is there within the accumulator lower word, that content will be pushed onto the top of the stack. That content will be pushed onto the top of the stack. So this is about the push and pop instructions. So what is the use of the push and pop instructions? They are especially used in accessing the stack area. They are especially used in accessing the stack area. Not only that, in the previous classes, I would have told one more point also that when you are writing one program, let us suppose you are writing the C program, then you are declaring the variables in the declaration part of the C program. Then all those variables are means declaring the variables in the C program is nothing but requesting the microprocessor to allocate some space in the stack area. Okay. So when you are finishing your main program means you are popping all the details, means you are vanishing your stack which is allotted for the program which you executed. Okay. So that is what the push and pop is concept and the stack concept which is useful in during the execution of a particular program. Now let's go to the RET instructions, written instructions. So we are having the normal written instructions as well as we are having the conditional written instructions. Means if the condition is satisfied, then only return from the subprogram. Otherwise, no need to return from the subprogram. And also we are having the interrupt service written instructions. Normal written instructions means if you are writing one subprogram for a normal operation, means let us suppose I would like to perform the multiplication operation using the DSP processor. Then what I'll do is a DSP processor, and also I'm having the request in such a way that you should make use of the subprogram concept. Then what I'll do is I'll just declare two variables in the main program, and after that I'll call the subprogram. In the subprogram I'll perform the multiplication operation. Again I will come back to the main program. Okay. So when you are coming back, means when you are supposed to divert that, means when you are having the main program as well as the subprogram. First of all, in order to divert the execution control from the main program to the subprogram, first of all you should have used one of the call instruction. I'm assuming that it is a CALL instruction. Otherwise, you can use the CC instruction also, which we have seen in the few minutes back. Okay. So when you are calling this one, then obviously it will enter into the subprogram. And before finishing your subprogram, means your subprogram should be finished with one instruction called as a RET, written from the subprogram. This RET instruction indicates that we are returning from the subprogram to the main program. And we will continue the execution in the main program. We will continue the instruction main program. So this is a normal subprogram. Let us suppose we are writing the subprogram for the interrupts. So interrupt is nothing but what? It is a request coming from the internal or external sources. Okay. So it is a request coming from the internal or external sources to perform a particular operation. So when you would like to perform a particular operation to a particular request, you should write the separate subprogram. Okay. So when we are writing a subprogram for the interrupt, that subprogram is called as it is simply called as a ISR. All of us know this one, right? ISR. Okay, so it is simply called as a ISR. ISR is nothing but the interrupt service routine. When you are written, let us suppose this is my subprogram for this particular ISR. Means I am calling this one as a subprogram. So I'm not considering this part now for the explanation point of view. If at all this is a subprogram written for the a particular interrupt, then I can't use the RET instruction. Means I can't use the normal RET instruction to return from the interrupt service procedure or the interrupt service routine. ISR is also called as a interrupt service routine or the interrupt service procedure. So we can't use the normal RET instruction to return from the ISR to the main program. But we are supposed to explicitly mention that whether we are returning from the interrupt or the normal subroutine. If you are using only the RET, then we are returning from the normal subprogram. But if you are returning from the interrupt, then you should use the other RET instruction, which may be some processors are using the RETI instructions to indicate that returning from the interrupt service routine, or some other processors are using the IRET instruction to return from to indicate that we are returning from the interrupt service routine, not from the normal subroutine. Okay, now so let us see all those instructions. Wow, what kind of instructions we are using. So whatever the RET instructions we are having, whatever the RET instruction we are RET instruction we have, this particular RET instruction is used for returning from the normal subroutines. Returning from the normal subroutines. As I told you that when you are coming back from the main program to the subprogram, the top of the stack will be popped into the program counter. Not only the program counter, other registers also there, which are which are restored back into the means some of the values which pushed onto the top of the stack when it is entered into the subprogram and finishing the subprogram and coming back to the main program. Those values are popped from the top of the stack and saved into the what is that respective registers like program counter, accumulator, status registers, all those things. Okay. So yeah, those registers that purely depends on the type of the what is it call instruction and if it is an interrupt instruction, obviously lots of registers contents are pushed onto the top of the stack now. Okay, now if you get confused, you just leave that one because it is quite different. But remember that not only the program counter, we have some other registers. If you want to remember simple way, it is a status registers. We have the status register 0 and the status register 1, right? So those registers are means only few registers are pushed onto the top of the stack if it is a normal subroutine. If it is a interrupted subroutine, then lots of registers content are pushed onto the top of the stack because those registers may get altered during the execution of the ISR. During the execution of the ISR. Okay. So another case is the RETC instruction, means returning from the subroutine only. It is from the normal subroutine only, but by checking the condition. If the condition is satisfied, then only return from the subroutine to the main program. Otherwise, don't return from the subroutine to the main program. That is the RETC instruction. And we have the one more instruction called as a RETD instruction. So this is a two-word instruction or two one-word instruction following the RET instructions are fetched from the program memory and executed before the execution of the return statement. Okay, now so means when the RETD instruction executed by the microprocessor, that's the DSP processor, before diverting the execution control from the main program to the from the subprogram to the main program, it may execute the one or two instructions. It may execute the one or two instructions that is indicated by the RETD instruction. And as I told you that we are having the one more instruction called as the RETINA, returning from the interrupt. As I told you that from the processor to processor, the mnemonic name will change, but the concept won't be changed. So because I told you that we may have the we may use IRET instruction to indicate that returning from the interrupt, or we may use the RETA instruction to return from the interrupt service routine. Okay, now that purely depends on the type of the processor. But in case of the DSP processor, in case of the DSP processor, we are using the RET instruction. In case of the TMS326 processor, we are using the RET instruction. So as I told you, that lots of registers content are pushed onto the top of the stack when you are when you are calling the subroutine. Upon the returning also means during the calling operation, means when the interrupt is occurred, all these registers are pushed onto the top of the stack now. During the when the interrupt is occurred, all these registers contents are pushed onto the top of the stack. Okay. Now. And when you are returning from the subprogram to the main program, again these registers are means the values which are pushed onto the top of the stack now. Again those values are recovered or loaded back into the respective registers. Loaded back into the respective register to resume back into the main program with the previous status. means just before leaving from the main program, what was the status of the main program, that in order to resume back to that particular status, again these contents are retrieved back into the respective registers when you are using the ISR concept, okay. So the next case is the repeat instructions. So we are having the RPT, and this particular repeat instruction is used to repeat a particular instruction for finite number of times, or I can say that it is a count number of times. So in order to repeat means repeat instruction is used for repeating a single instruction, actually repeating a single instructions by the count number of times. So that count value is there in the RPTC instruction. That count value is there in the RPTC instruction. RPTC instruction is the one which is holding the repeat count value. Means how many times you would like to repeat a particular instruction, which is stored in the memory location, or which may be indicating using the indirect addressing mode or the direct addressing mode. So that particular instruction get executed by the RPTC times, by the finite number of times, or I can say that the count times. That count value is stored in the repeat count register. That count value is stored in the RPTC, which is a repeat count register. So we are having the two types of addressing modes now. Let us go upward. You are having the four types actually. One is the direct addressing mode, RPT, another one is the indirect addressing mode, and another one is the immediate addressing mode only, but we have the two types of immediate addressing modes. One is the 8-bit, there is a short immediate addressing mode and the long immediate addressing mode. Short immediate addressing mode and the long immediate addressing mode. So as I told you that how many times you would like to execute a particular instruction, that count value should be loaded into the RPTC register. So whatever the instruction you would like to repeat for finite number of times, the count times which is saved in the RPTC, that instruction should be preceded with the RPT instruction. Okay. So the next case is, that's what we are having. So direct or indirect addressing mode. The DMA is indicating the count value. That count value is stored in the RPT. So directly you can specify the count value, how many times, how many times you would like to repeat that particular operation, that should be taken as a count, and that should be loaded into the RPTC register. Okay. So the next one is a peripheral control instructions. Peripheral control instructions are nothing but peripherals are nothing but we have in case of the DSP, in case of the microprocessor, we don't have the 8086 microprocessor actually. In case of the 8086 microprocessor, we don't have the on-chip peripherals, but in case of the DSP processor, we have the on-chip peripherals as well as the off-chip peripherals. Okay. So on-chip peripherals as well as the off-chip peripherals. When you would like to access the off-chip peripherals, which are interfaced to the microprocessor, in order to access those peripherals, you are supposed to use the in and out instructions. It is just like a port addressing mode in 8086 microprocessor. We have seen the port addressing mode in a 8086 microprocessor. Now there we studied about the two instructions called as a in and out instructions. With the help of these two instructions, we are able to read the information from the input port as well as we are able to write the information onto the output port. What I mean to say that here I'm having the peripherals now. So I'm not going with the on-chip peripherals, I'm going with the off-chip peripherals. So I'm assuming that this is the DSP processor, this one is the DSP processor, and this one is the IO device, input-output device. When you would like to perform, when you would like to read the information from the IO device into the DSP processor, or when you would like to write the information from the DSP into the IO device, you are able to perform you are able to deal with the IO devices with the help of the two instructions called as a in and out instruction. But when you are interfacing the IO device to the microprocessor, we are using one thing called as a port. Okay, means when you would like to interface the external peripheral device to the DSP processor, you should allocate some port, right? Port is nothing but that particular port is also having the some address. Means with the help of the port address only, we are able to transfer the information via that particular port as well as receive the information via that particular port. Okay, so means the port address plays a major role. So means when you are using the in and out instructions, you should mention the port address through which port you are performing the read data operation on the input output device into the microprocessor or out of the microprocessor. So that is done with the help of the IN, DMA, PA. So IN, DMA, PA is nothing but reading the information from the port address. PA is nothing but the port address into the data memory address. Reading the information from the port address. From the port address means which is interface to this particular IO device. Na? From there into the data memory address. From there into the data memory address. For that we are using the in instruction. So means you should mention the data memory address you would like in which memory location you would like to store the information which is read through the port, right? So here, when you would like to perform, when you would like to read so many bytes of values or the words of values from the input device into the microprocessor using the IN instruction, you can simply make use of the RPT instruction. Okay. So this is about your in instruction, and the next one to write the information onto the output device. We have one more instruction called as a out instruction. Out instruction to write the data from the DSP processor onto the output device. Again, we are having the operation is reverse. We are writing the data from the data memory onto the port address. So when you are writing the information onto the port address, that will be written into the output device. So this is about your instruction set of the DSP processor. So I think we left with the norm instruction. Okay, now we'll continue the norm instruction in the next class along with the addressing modes. So you in the next class we'll finish off our fourth unit by studying about the norm instruction, NORM, which is a normalization instruction, and the what is that addressing modes. I'll try to finish up the concept in the next next video class. So with that, we'll finish up the fourth unit in the microprocessor. Okay. So if you are having any queries regarding this particular class, so let me know in the group. As well as if you are interested, you can comment in the what is that YouTube itself. Okay. We'll continue in the next class with norm instruction and addressing modes.